Here's the question I posed at the end of the previous part of the lecture. If you had any trouble answering this, it's telling you that you need to work on your trigonometry. In any case, all you really need to do is draw the triangle that you use to decompose this vector into its components. And the triangle shows you how to do the trig. And so the answer is B, although I'll point out, as usual in these sorts of questions, you didn't even really need to do the calculation. Clearly C and D are wrong because the direction of the velocity vector shows us that both components must be positive. And A can't be right because with the 60-degree angle, the y component of V must be bigger than the x component. Now, it may not be obvious to you why we wanted V in component form instead of magnitude direction form. The quick answer is that in a moment we're going to need to add vectors, and we only know how to add vectors when they're in component form. So now let's think about the airplane at some location at some time t, any time, and where it will be 1 second later. Well, we certainly know, because it's going 200 meters per second, that in 1 second it's going to go a distance of 200 meters. This is going to allow us to find how far it goes in the x direction and how far it goes in the y direction. We can just draw the triangle, and now do a little bit of trig, and again we know how far it's gone in the x and y directions. But what we've just found are the components of the displacement vector at that time. And so we can just write down that displacement. This isn't all that useful yet because it's specific to 1 second later. What if we want to know what its displacement is at some other time? Well, notice that if we wait longer, then it will have gone farther. For example, if we wait twice as long, then each of the x and y components of the displacement ought to be twice as big. In fact, all we need to do is find our displacement by multiplying the velocity vector by delta t. Now we're almost done, but what we want is not really displacements. What we would like is to be able to write down the position of the plane at any time. So let's think about the relationship between the positions and the displacement. The triangle shows you, since Ri and delta r are head to tail with each other and point to the same place as Rf, that Rf must just be the vector sum of Ri and delta r. So we can replace delta r with v delta t, and we have our final answer. For motion in an arbitrary direction at constant velocity, we can write the position at any time in terms of some earlier position plus v delta t. The one remaining thing is that it would be nice to be able to write this in some other forms. Think back to lecture 3, where we saw this equation for motion at constant velocity along the x-axis. Now, it looks an awful lot like the equation that we just got, and there's a good reason for that. Let's expand all of these vectors out into their components. And now let's collect terms. So we collect all the I hats and the j hats on the right-hand side. Now, you can just pull out the I hats into one equation, and you can pull out the j hats into another equation. And notice that this equation down here for xf is exactly the one we saw back in lecture 3. And so we can rewrite this vector equation as two component equations. And you should get used to this. We can usually write things compactly as a vector equation, but sometimes it will be more useful to split it up into the equations for the individual components. Let's check that you understand how to use this. An air puck is like a little toy hovercraft. It hovers above the ground on a cushion of air, and it moves with very, very little friction. And so, to a very good approximation, it moves with constant velocity. So suppose we have an air puck moving with this velocity, and at some time, t equals 2 seconds, it passes through this position. Figure out where it is at t equals 5 seconds.